The matrix has many applications, but for our purposes, its most useful application will be solving systems of linear equations. So let's use a matrix to solve this system. So the first thing we'll do is we'll line up all the x's so that they're in the first position, all the y's so that they're in the second position, and all of the z's so that they're in the third position. And then we're going to bring all the constants over the right-hand side. So the first equation is conveniently already done for us. We have 3x plus 4y minus 2z is equal to 6. The second equation we're going to have to rearrange a little bit. We'll have 1 times x, switching the x and the 2y around, because there's understood to be a 1 right here, right? So we put the 1 in front, plus 2 times y. And there's no z in this equation, so we're going to put a placeholder. We're going to put plus 0 times z, like this. And then bringing that 4 over to this side, we have it's equal to positive 4. Then we have 0 times x, because there's no x in this equation, plus 1 times y minus 7z equals, bringing the 7 over, 10 minus 7 is 3. So this system of equations can now be represented by a matrix. And that matrix will look like the following. It will have a 3, a 1, and a 0, 4, a 2, and a 1, minus 2, 0, minus 7, and then 6, 4, and 3. So a matrix is basically just a spreadsheet that has different cells where you can input different values. So on this side of the matrix, we just input the coefficients in front of each variable. We see that we have 3, 1, 0. There's a 3, a 1, and 0 in front of the x's in this column. And then 4, 2, 1, so 4, 2, 1, and then minus 2, 0, minus 7. And then the constants go on the right-hand side. Now in the language of linear algebra, we say that this 3 by 3 matrix on this side is called the coefficient matrix, in that it represents the coefficients of the system of equations. And that this column of constants augments that coefficient matrix. So in terms of row by column, number of rows by the number of columns, we have 3 rows and we have 4 columns, right? Okay, now we're going to use our calculator to solve this system of equations, to solve this matrix. And you go into your matrix editor and you input these values into this matrix. So the first thing you do is you tell your calculator how many rows and how many columns. And you can see the tutorial below this tutorial on this page of how to use your calculator to access your matrix editor. So you access your matrix editor, you input the number of rows and the number of columns, then you fill up the matrix with these values, right? And then once you have your matrix, right, with all the values input, you go back to the home screen. And you come back to the home screen and you type in RREF, which stands for Reduced Row Echelon Form. And we're gonna learn what's going on behind the scenes in just a moment, but first we're gonna use the calculator to solve the system. So RREF, and then open parentheses, and then whatever the name of your matrix is. I call mine M1. And then you hit enter. And then the resulting matrix will pop up on the home screen. You have a 1, a 0, a 0, a 0, 1, and a 0, a 0, a 0, and a 1. And then minus 2, 3, and 0. Like so. Let me check this. That is correct. Okay, so let's take a look at what this new matrix is telling us, because I'm going to make a claim. I claim that this new matrix, right, is in essence conveying the same information that this original matrix was conveying. And let's take a look at what this new matrix is telling us. So the way that the matrix speaks to us is it says the following. Let's take a look at this first row of this matrix. It says 3 times x plus 4 times y minus 2 times z equals 6. Well look, that's just this first row here. 3x plus 4y minus 2z equals 6. So the new matrix speaks to us in the same language, the same way. This one says 1 times x plus 0 times y plus 0 times z equals minus 2. So x equals minus 2. Then the second row says 0 times x plus 1 times y plus 0 times z equals 3. So y is equal to 3. And then the third row says 0 times x plus 0 times y plus 1 times z is equal to 0. So z equals 0. So we have solved the system, right? So in terms of, this is the x column, the y column, and the z column. And this is you know, you come down to the 1, this is x, this is y, and you come into the z column and come down to the 1, and this is z, so z is equal to 0. And that's it. We solved it with the push of a button, just like that. So let's take a look at what's going on behind the scenes, what the calculator is doing. So if we multiply this first equation times negative 1/3, right? Times negative 1/3 on both sides. If you do, you know, the first rule in algebra is what you do to one side, you have to do to the other, right? We haven't changed that first equation in any way, because we could just as easily divide out the negative 1/3, and we haven't changed it in any way, right? We could, and note that that's the same thing as multiplying this first row times negative 1/3, because this negative 1/3 distributes through to each position. Then we could add that result, right? The result of multiplying negative 1/3 times each value, right? Negative 1/3 times each value here. Add that result to row 2. And that's legal to do. We can add equations together, right? So look what would happen if we did that. We would do negative 1/3 times 3, which is negative 1, plus 1 gives 0. So now we would have a 0 right here, right? So then we'd have 3, 0, 0. Then we can multiply the first row times 1/3 and just leave that row in its place. And we would have a 1 here, a 0 here, and a 0 here, right? So 1, 0, 0. So the row operations, and this is what these are in the language of linear algebra, these are called row operations. The first row operation would be negative 1/3 times R1 plus R2. And then whatever this result is, this operation gives, we replace R2 with that, right? And you do that for each corresponding entry. So, you know, negative 1/3 times 3 is negative 1 plus 1 gives a 0, so you have a 0 here. But then you do that for every entry in the matrix. So negative 1/3 times 4 is negative 4/3 plus 2 gives positive 2/3. So you'd have a positive 2/3 right here. So you have a 0 here, a positive 2/3, and then corresponding entries, you know, along the row, right? As you perform the row operation on every column. Okay. So the second row operation that we made note of is we just multiply 1/3 times R1 and then we left it in that place. 1/3 times R1 left in R1, so we had 1, 0, 0. And your calculator iterates and does these things systematically and repetitively so as to achieve 1s on the diagonal with 0s everywhere else and the answers on the right hand side, right? So at first it does the first row first, the first column rather. It operates in terms of the algorithm. The algorithm will operate and take care of this first column first, then it'll do the second column, then it'll do the third column. And you'll end up with this diagonalized matrix, as we say, with 1s on the diagonal, right? Okay, so this method is essential for scientists and engineers to have earlier in their academic careers because it will be used over and over to solve systems of equations. Note that we could have, instead of 3 rows, we could have n rows, right? Then we would have n plus 1 columns because the 1 is there because the constant's on the right-hand side. So you could have a system of 15 equations with 15 unknowns, and you could solve it just like that, right? Very powerful and useful method. I encourage you to learn it and to apply it frequently. You're much less likely to make errors and so on. So there are some exceptions to the matrix where the matrix will not reveal a unique solution, and those exceptions are covered in the matrix caveats tutorial. So I encourage you to go take a look at the matrix caveats tutorial because you need to be aware of those mathematical situations that will arise. Okay, I'm going to step to the side and give you a clear screenshot. Try it for yourself.